Next speaker covers more than 45 years, and it'll be a challenge for Bill, but he has 45 minutes. And what I'd like to do is read a short biography of Bill's and then add a few things because it was too short. Bill Smith, after receiving his PhD in 1966 and spending 11 years in the District of Columbia involved with Nimbus and the TIROS-NOAA series of polar satellite sounding instruments, Bill Smith returned to the UW in 1977 with a small group of NOAA scientists who worked with Professor Suomi's staff to build a data processing system for the Visser atmospheric sounder, and Hank was talking about that. It was first flown on GOES-D in 1980, so that's a lot of years ago. This was when Bill met Hank, and they started working together on the hyperspectral sounding program that will be described in this presentation. As Bill will explain, Hank was the leading force behind the successful implementation of the aircraft surface-based and satellite hyperspectral interferometer sounding instruments during the past 41 years of working together. What's not on this short bio is that the partnership that Hank and Bill had was certainly preceded by the partnership that Bill had with Vern Suomi. And when Bill came back, he came back with a team of NOAA scientists, and Vern liked that so much, he said, let's make this more permanent, and that's how SIMS came about, the Cooperative Institute for Meteorological Satellite Sounding. So in many ways, hyperspectral sounding that Bill envisioned that we didn't get on VAS is sort of the birthplace for SIMS. So Bill, if you could come up here and clean up the introduction I just gave for you, I would appreciate it. The title of Bill's talk is Henry Revercomb, The Evolution of the Infrared Hyperspectral Remote Sensing Technique. Or techniques, it probably should be. They never settled on one.
Okay, thank you, Paul. Appreciate the introduction and pointing out probably the most important relationship that was initiated regarding this effort was the SIMS creation and the inspiration really of Vern Suomi of doing that. In any event, I'm a sounding guy, not really an instrument guy, and I was educated as a meteorologist, so my real interests were in applications of data, not in building instruments to do it. But I found early in my career, after Vern told me to go get a year's worth of experience in Washington and then come back and work with him, that I had to learn about instruments in order to get the kind of data we thought was needed for the applications. But everything I learned about instruments were from very intelligent people who knew a lot about them, and Hank was certainly the most inspirational one that I dealt with over my years of working as a scientist on this problem of atmospheric sounding. This talk is really a tribute to you, Hank. I cannot thank you enough for all that you've done, for all of us really that are in this sounding business, because without you, it just would not have happened, not the way it has. And as was mentioned by Paul, it was in 1977 that I returned to the university after spending not 1 year, as Vern envisioned, but took me 11 years to do what he thought I might be able to do in 1 year. But then it was an exciting 11 years. But then with the VAS program, and Vern and I were both working on VAS, but from a distance. And I had my group in Washington working on VAS. It was a great innovation of Vern's to take this sounding technology that we had demonstrated under the Nimbus program and put it on a geostationary satellite to get dynamic observations. And so I was working on this and had part of my group there working on this. And of course, Vern had his team here working on VAS, as Hank had mentioned earlier, with Larry and others. And so Vern said, you know, it's silly for us to be working apart. Why don't you come back to Madison now and we'll do this together? And I said, great. In fact, my kids were just getting to high school age, and you know, with all the drug problems and so on in the big city, I said, yeah, it's time to go back, get out of this environment for my teenage children. Well, that was a personal motivation to come back, but the professional one was always there. I had always intended to come back here to the university. So I came back, and I brought a number of people with me, some of my very best. I had a group of about 30 people, and only brought about, well, really, the 6 best individuals with me to here to work with this creative group that Vern had established. And so we came to build the data processing system for the Visitor Atmospheric Sounder in 1977, and that was to be launched in 1980, and so we had our work cut out for us. And right before this, as I'll explain in a moment, it was brought to my attention that there was another way of doing this sounding business. And I'll go into that in the very next slide. Let's see, I guess you... But in any event, we realized, even when we started working on the data processing system for VAS, that it wasn't really going to work the way we had envisioned, and that what we were after, used these geostationary soundings to get the environment for the development of severe weather, severe storms, tornadoes, that kind of weather. And whereas these low vertical resolution instruments we were flying on polar orbiters could give you large scale information, which were good for global dynamic models and so on, it really lacked the vertical resolution needed for sounding the atmosphere to get atmospheric stability, convective instability, and things of that nature that you need to predict severe storms. We had very high time resolution, very high space resolution, but we had very poor vertical resolution. So we saw right away that the VAS poor vertical resolution was going to be too limited for mesoscale sounding applications. And so that then started this hyperspectral sounding program. And what I'd learned right before I came back here was Tom Kyle visited me. He was a scientist, and he pointed out that whereas radiance is broadband or even narrowband, but just radiance by itself measures the thermal emission from a deep layer of atmosphere. And so it's very limited resolution. But if you looked at the Fourier transform of the spectrum, or what we call the interferogram, that there's signal in there that are related directly to the vertical structure of the atmosphere. And that is these resonance regions which occur if you have lines which are uniformly spaced in the spectrum, like CO2 lines. And you get these resonance regions that only occur if you have vertical structure. This is the signal of the interferogram, and at 1 over the CO2 line spacing. And you see them here. And if there is no vertical structure, if the atmosphere isothermal, this signal would be 0. And so here you had a direct measure of the structure of the atmosphere, which is what we were looking for severe weather prediction. And so that, as soon as we landed here, my group from Washington, we said, we got to look into this. And we did. And so we simulated the interferogram of the spectrum and related that to the atmospheric vertical structure. And there was a paper published pretty early on. It took us 2 years to get it on the street, but that showed that you could, by just measuring the signal on these resonance regions, you could get vertical temperature structure and thereby get errors that were more than 1 degree smaller than what you get with radiometers, like we were going to get with VAS and so on. So that was a huge finding. And so we teamed up with Hank and his group. Let's see, how do I move this along here? There we go. Nope, that's not the one I want. I'm now going the wrong way. Do you point this at something? Huh? Oh, I see. Okay, let me. There, John, I'm lost.
Go backwards.
Yeah.
So this should go backwards. And this button here goes.
Oh, that one. Okay, I had pushing the wrong button. Thank you. Okay, so in any event, I'm missing a couple of slides here for some reason. But in any event, my team worked on then the theoretical aspects of deriving soundings from partial interferograms. And Hank and Larry worked on developing instrument techniques for getting the measurements. But we decided, and it was really Hank's leadership which led to the fact that we really needed to measure the whole spectrum, not just pieces of the interferogram. We need to do it with high resolution. That was mainly because water vapor lines are not uniformly spaced in the spectrum. And so you do not have these resonance regions with regards to water vapor signal. You need, the signal is throughout the interferogram, so we need to measure the entire, a large length of the interferogram and use the spectrum to get water vapor profiles as well as temperature. And that led us then to defining a interferometer, or a Fourier transfer spectrometer, which Hank already talked about, called the HIS, which we proposed then to NOAA and NASA in 1980, and they jointly funded the development of the HIS aircraft instrument, which Hank already talked about. And as Hank mentioned, this was flown in at first in the NASA ER-2 aircraft, and truly, Hank is the guy who really made it work. Of course, he had a great team of people, as he mentioned earlier, working with him on this, but he really made it work. And most of all, he published a paper on how to calibrate such a device, and it's a very important paper that's used by everyone who deals with interferometers, Fourier transform spectrometers of this type. It's the fundamental way of calibrating all the interferometers that we're flying in space today. So I want to point that out. That is really important. And so that was very successful in that we then flew this, and we flew it in many missions, as Hank had pointed out in his talk. But it really did show that by measuring the spectrum at high resolution, you could get high vertical resolution details of the atmospheric structure. This is water vapor that was measured on about a 75-kilometer length path over the ocean, and went across an island where we had a radiosonde released here. This is the radiosonde relative humidity measurement. And this is the HIS derived water vapor structure, 0 to 20 kilometers along this path. And it's phenomenal what you can see here. You can see all these vertical features that were retrieved from the Fourier transform spectrometer data in the radiosonde observations, such as this moist layer up in this region. Even this dry layer, if you see it here. And then this is the boundary layer region. This is only up to 2.5 kilometers, the marine boundary layer. And you can see this moisture at this level at about 2.5 kilometers in the radiosonde. And then another moist layer just above the surface, which is in the radiosonde data. So it really did prove that this concept worked. And that's, again, thanks to Hank's leadership in building an instrument to demonstrate this, this capability. And we flew this instrument, as Hank mentioned, on many, many different field programs, but one which was out in the middle of nowhere. There weren't any other measurements. We were flying on the NASA ER2 out of Christchurch, New Zealand, and we were flying from Christchurch to the south, towards the South Pole, over Antarctica. The pilots were very brave because, you know, if there's any aircraft problem in the Southern Ocean, especially towards Antarctica and so on, there's no hope for recovery. They were gone. They were risking their lives greatly by doing these missions. But we flew the HIS instrument on the ER2 during 4 seasons to study the Southern Hemisphere winter polar vortex and how it changed with season, this polar vortex. And I just show the vertical cross-section for April, which I guess would be fall in the Southern Hemisphere, and midwinter, August, derived from the HIS data. And no other data was used. There wasn't any other data to use. There weren't radiosondes or anything like that along this flight track at all. And you can see the vertical detail that was retrievable with the HIS data, especially the characteristics of the winter polar vortex. This is at near the South Pole here, 87 degrees south latitude. And the reason you see the mirror image here is because what's shown here is the flight from Christchurch to near the South Pole and then back again to Christchurch. So you should have nearly a mirror image except for the time change that took place there. And any event, that was also, I think, very convincing to many that these were indeed very important vertical structure data that you could get with hyperspectral remote sensing using an FTS system. And then, well, we couldn't get it on GEO. We kept trying to move this to GEO, but we did have an opportunity to propose for the EOS polar platform. And the instrument to fly on that platform was called AIRS, and NASA requested 2 proposals for that instrument. One to come from JPL, which was a grating spectrometer approach using very large focal plane detector arrays, each detector measuring a different spectral channel, and the FTS approach, which was already demonstrated on the HIS. In fact, it was the HIS data which led to the approach, regardless of whether it was a grating instrument or an FTS, to measure the entire spectrum, to measure the spectrum of infrared radiation with high spectral resolution so that one could get high vertical resolution profile information. And Hank, again, led the technical effort on our AIRS FTS approach proposal. And it was kind of a unique proposal. It had some capability that we probably should get back into the system today, such as measuring with very high resolution, 0.2 wave number resolution, the band head of the CO2 band. This is just a very narrow region on the short wavelength side of the 4.3 micron band, which gives you very high vertical resolution in the troposphere of atmospheric temperature. And then we had the more conventional, his types of bands. These are just the temperature, but we had broadband water vapor too. It covered pretty much the entire spectrum from, I think it was about 3.5, 4 microns to 15 microns. Now that, unfortunately, for us, was not accepted. JPL won that with the grading concept, but although it was not accepted for EOS, our proposal, his heirs' proposal, was the basis for the METOP-IASI instrument. In fact, Europe essentially said that, well, if the US isn't going to fly an FTS, we will. And that was at the urging of Bizzari, who actually presented our proposal at one of the European meetings looking at advanced instruments for space. So that had a very positive benefit in that we got METOP-IASI, which is also a very good instrument, FTS instrument on 2 METOP satellites flying today. And then the same year, in 1988, was when we turned his upside down, and we took it out to Denver and put it next to a microwave system that was looking up, and to demonstrate that with high-resolution infrared, we could also measure the boundary layer characteristics by looking up. So we turned it upside down and demonstrated this high vertical resolution capability. These are comparisons between a radiosonde, which is called the CLASS system here, the DASH, the radar acoustic sounder, the RAS, the HIS is the solid line here, and a microwave profiling radiometer, which is this dash, large dash line here. And of course, that success then led to the development of the ARI instrument, and the DOE ARM program was what really enabled the atmospheric emitted radiance instrument to Hank was PI of a proposal to the DOE ARM program that got funding for developing ARI, which had, was really ruggedized for these kinds of measurements from many, many ground sites around the Earth. And so Fred Best, of course, was very instrumental, and no pun intended, but is very instrumental in making this concept work as well under Hank's leadership. And that same year, that 1990, when our first ARIES went into operation, we tried again to get the interferometer, the hyperspectral instrument on a geostationary satellite with a proposal called GHIS, which was very novel in the sense that we took the existing sounding instrument for GOES, removed the filter wheel that it was using, and placed in this place a Fourier transform spectrometer to give very high spectral resolution. And NOAA did this. In fact, it planned to fly it on the first 3-axis stabilized geostationary satellite. And ITT, which is Harris now, and MIT Lincoln Lab, actually built a prototype of this instrument, an actual GOES filter wheel sounder, removed the filter wheel, changed the optical system to employ an FTS, and demonstrated the concept in thermal vacuum. But here again, we failed to get it in space. This canceled the program because the administrator at that time, I won't mention any names, I will in private afterwards if you want to know who it is, but decided he got cold feet. He got cold feet, and he thought the risk of flying a new instrument like GHIS on the first 3-axis stabilized operational GO satellite was too great a risk for him to take anyway. And at that time, they were having problems with the stabilization system. And so I think if they hadn't had those problems, it probably would have got up there. But he got scared. He said, we can't get the stabilization system to work, and then what happens if the instrument doesn't work? So he chickened out, and we still didn't have it in space. But we saw another opportunity. What did I do here? Yeah. We saw another opportunity then we said, okay, let's go back and at least get rid of the HERS instrument on the polar satellite. Replace that with an FTS. And so we developed what we want to replace HERS with ITS. And as Hank pointed out, EUMETSAT got very interested in this opportunity and funded the Phase A study to develop an instrument that could fly on the NOAA satellites in place of the HERS. And so that proposal was prepared in 1991 and was submitted to EUMETSAT, who funded the Phase A study for this. And the study lead was our leader here, Hank Revercomb, again. And he was responsible for leading the way on developing an instrument approach that could do this. And as was pointed out by Hank earlier, since we're going to fly it on a NOAA satellite, the size of the instrument, the ITS, which turned into the CRIS eventually, as I'll explain in a moment, had to be the same size as the HERS instrument. But the data output and the data quality as well as the data quantity was quite different. Instead of just, about 2 dozen, not even 2 dozen, 1.5 dozen broadband measurements as shown here in the spectrum, very smooth and so on. We had an FTS instrument that was producing HIS-like high resolution spectra. And so 712 channels on ITS versus 12 channels in the infrared spectrum on the HERS. And it was the more spectral channels, of course, that had already been demonstrated with the aircraft systems, which made the difference in vertical resolution. And this didn't go until the NPOS program came along, and they were looking for a sounder to fly on the NPOS system, which was the next generation. The satellite to follow the NOAA satellites was to be called NPOS. It's not what we call JPSS, so because NPOS as a program actually was terminated some years ago. But anyways, when the NPOS needed an atmospheric sounder, and they looked at different designs. I think they would have taken the instrument if NASA would have provided it to them cost-free, but NASA wouldn't do that, so they looked, and the cost of buying an AIRS was quite high, and so they looked towards another approach, which was this ITS design. And that's why the CRIS is just like the ITS that was in that original design study in 1991 with the 3x3 detector arrays. It's actually more like 14 kilometer resolution instead of 10, but we actually had an 8 kilometer resolution proposal for the NPOS, but they took the lower resolution, unfortunately, and the bands are about the same. And so this picture here is actually taken from our design feasibility study for the ITS instrument. And the other thing we had to do was keep the data rate low in order to get the data down from the NOAA spacecraft. And so this is where this concept of reducing the resolution of the data by truncating the interferogram at different limits, the midwave and shortwave came. It was purely to reduce the data rate, to fit it in the HERS data stream. It didn't do it in the long-wave band because we had to pick up these resonance regions, which gave us that very high vertical resolution temperature profile information. And when the NPOS program adopted this instrument, we told them not to do this. There's no need to do this for NPOS. This was a HERS design. But they wouldn't listen. They said, well, if it was good enough for the NOAA satellite, it's good enough for NPOS. And we tried and tried and tried to get them to not do this, to go full resolution for all 3 bands, but they didn't do it. And so we flew the instrument like this, except, fortunately, there was a mode on the CRIS instrument to get full spectral resolution for all 3 bands for calibration purposes. So after it was realized, after the first CRIS on SUMI NPP was in orbit, and people were complaining about the spectral resolution in these other bands, like for getting CO and other properties, NOAA decided, yes, let's put it in this full resolution mode. So now we do full spectral resolution from CRIS in all 3 bands. So CRIS turned out, because of our ITS development, to be the smallest of all the hyperspectral sounders we're flying in space today. You can see how much smaller it is than IASI or AIRS. Not only that, it's the most accurate. You can see this from the noise curves for the 3 bands. The black being the CRIS instrument, the red being the IASI instrument, and the blue points here being the AIRS instrument. So this is a phenomenal achievement. And again, it's Hank's leadership in the design and calibration of the ITS and CRIS instrument. It's the major reason for the success of our CRIS instruments that we're now flying on SNPP and the JPS satellites, the one up now and the several to follow in the future. So thank you, Hank, for that. And the same year that 1995, that we proposed the ITS instrument, or after that, I'm sorry, that was 91, this is 95, is when ARI went to sea. We took it out in the sea to see how well we could measure the ocean temperature and the ocean emissivity. And we also, under Hank's leadership, flew the NASA ER-2 aircraft with the HIS instrument on it, which would tell us if we could measure sea surface temperature and emissivity very accurately with an interferometer that was very close to the sea, how can we do that from space? And we wanted to demonstrate that with the aircraft. And so with the ARI, we were able to demonstrate that you could get sea surface temperature to better than 1/10 of a degree, which was far better, almost 5 to 10 times better than what we were doing with spacecraft measurements at that time, which is more like a 1/2 to 1 degree accuracy. This was 1/10 of a degree. And we did that by being able to measure from the sea with the ARI the angular distribution of radiation, and then account for the emissivity contribution to the radiance as a function of angle, geometry, and sea state. And this led then to the development of the MARI instrument, the marine ARI, initially funded by NASA to validate EOS measurements, but now being used for scientific studies on many research vessels. And since we had simultaneous aircraft measurements and so on, we were able to demonstrate, or improve anyways, the accuracy of sea surface temperatures from aircraft at that time, but eventually from the hyperspectral sounders in space that we're flying today. And as was mentioned earlier, the NAST-I and the Scanning His program, Scanning His instrument programs were very influential in being able to prepare for the application of these hyperspectral data from space, AIRS, IASI, and CRIS that were to come, and for validating data from these satellites once we're in orbit, as I'm sure Tom Bacano will tell us in his presentation how important these instruments were for preparing for AIRS and in the validation of AIRS. And we also, with the aircraft having scanning measurements and so on, we could fly patterns aircraft to simulate geostationary measurements of hyperspectral data and demonstrate this concept of providing vertically resolved wind profiles from geostationary satellites. And of course, that led to the GIFS instrument. And when Hank mentioned that Bill Smith went to NASA to get this to happen, Paul leaned over and says, "What's he talking about? You went there to live on the ocean, didn't you?" But, no, I really did go there. We figured we had to be on the inside if we were going to get a proposal for our imaging FTS accepted by NASA, and it worked. It was accepted for the EO3 satellite. It was called GIFS, a phenomenal instrument, a phenomenal capability, and is being demonstrated actually today, and hopefully will be implemented soon, both by Europe and by the US, as Hank had mentioned. You know, our GIFS concept provided more than 80,000 atmospheric soundings every minute. There are 4-kilometer resolution spacing of those soundings. Incredible device, and it was demonstrated in thermal vacuum, looking at the atmosphere, looking up out of a thermal vacuum chamber, and looking up at the atmosphere and looking at the moon and so on, from Logan, Utah, where the instrument was actually built. And in the meantime, in 2013, that all took place in 1999 and throughout the early 2000s, well, mid-2000s as well. But then in 2013, Hank led an effort, atmospheric incubator effort, to develop the infrared component for the Clario system, a very important climate observation system. And this is going to be discussed further by John Jarrell, I think, and let's see, who else? Oh, Fred, of course. Oh, Joe, yeah, Joe. But I use concepts for absolute radiation calibration and so on that Fred Best had a tremendous role in developing. And actually, it was a concept to put a very high spectral resolution infrared interferometer in space with absolute calibration. These measurements would have internationally acceptable absolute calibration data. There's no need for calibrating these things on the ground by national calibrators whatsoever. And all the things needed to put a standard, an absolute radiometric standard in space. Very important, and will hopefully happen. And then we're still in the business after 41 years. We're still trying to get this thing US into geostationary orbit. So as Hank pointed out, in 2016, we developed another proposal under the Earth Venture instrument opportunities. I won't go into this now because I think I'm probably running out of time. Am I? Yeah. Or am I already out of time? I'm good, okay. Anyways, and this program had a fairly low cost cap on it, so we limited the the objectives. We're always accused of trying to solve all the scientific problems with a single instrument, the FTS. They'd say to Hank and I, you can't do everything with an FTS, can you? Of course, I'd say, yes, you can. So we tried to limit our objectives to the very important now-casting, near-casting application of atmospheric temperature, moisture, and stability data that we could get with a very high-resolution interferometer in space. And this instrument would have even greater capability than the GIFS instrument, in that it would be 2-kilometer spatial resolution, very high time resolution over limited areas, and also a high vertical resolution. And it was just the kind of data that was needed. And actually, the proposal reviews were pretty good, but it was not accepted. It lost to a JPL instrument. And so we're contemplating and planning to actually propose this for the next go-around of the Earth Venture Instrument class. Or, as Hank mentioned, there's interest in NOAA to accept this proposal that we've already put in. And if that happens, then we'll be certainly in orbit. And we'll be in orbit at a time when the Chinese put their next geostationary, or their operational GIFS-like instrument in space, which will have the full GIFS capability. And Europe, EUMETSAT, puts up the IRS, which is a GIFS-like instrument to fly on the Meteosat third generation, the MTG system. And so if we had all three systems in orbit, we would have very close to the global measurement capability that we want. In fact, that the WMO thinks is very important. We all think it's very important for the next generation global observing system. And the unique thing, one of the unique things of the geostationary measurements, besides getting high resolution temperature, moisture, and stability information for severe weather forecasting, is getting vertically resolved wind profiles by tracking water vapor as a function of altitude. And you saw from slides I showed earlier how high vertical resolution water vapor features can be resolved, so you can track those on pressure surfaces and get wind profiles from those data. And that's very important for global numerical weather prediction. But we'd like to have global coverage. So hopefully we will get a US system in geostationary orbit. And as Hank showed you, again under his leadership, the team here with Dave Tobin, Bob Knutson, and others were able to very accurately calibrate the GEARS data, which is the Chinese instrument. It's a lower spatial resolution instrument than GIFS, but it has the same spectral resolution and same spectral coverage of GIFS. It's 16 kilometers rather than 4-kilometer spatial resolution, but they were able to very accurately calibrate these data. And so when you take those calibrated data and apply our sounding algorithms that we apply to the polar satellites, such as the CRIS instrument, you get very accurate profiles, fairly accurate, comparable to what we're getting with the CRIS system. This is a comparison between GEARS and GIS over several hour time period, of course. These are multiple orbits that had to be put together to simulate the GEARS geostationary coverage, but they're very comparable in both temperature and in water vapor, as shown here. And so the Chinese, well, hats off to them for being the first to demonstrate the GIFS-like concept in geostationary orbit. And they're moving on. They have 2 more instruments they're going to fly, each one higher resolution. Their third one, which will be up early 2020s, will have full GIFS capability. That's the plan. In the meantime, over the US region, we're forced to sort of simulate the kinds of things we'd be able to do with a geostationary sounder by putting together polar with the GOES ABI data. GOES ABI doesn't have much temperature information, but it's got a significant amount of water vapor information at 2-kilometer resolution and spatial resolution and an up to 5-minute time resolution. And so the approach that we've taken here under support by NASA and NOAA, the NASA CARE program and the NOAA JPSS program, is to put these two sensors together, the data from these sensors, to get high spatial resolution and high temporal resolution temperature and moisture information. And the example that I show from this morning. This is data for today from this morning. We're doing this over the Wisconsin, Northern Illinois region and over the Virginia, North Carolina region, where we get, this is stability index here. Blue is very stable air, it's negative lift index. And red is very unstable air. Very stable over Wisconsin. Well, you didn't need the satellite to tell you that when you went outside this morning, did you? It's beautiful out there. And, but this is what the satellite data said it would be last night. This was at about 3 o'clock in the morning, 7Z UTC. And this is the difference between what the satellite shows and what the RAP, which is the operational, high-resolution operational rapid refresh system, the model that NOAA runs. It also shows where the satellite data is, and it's everywhere. So really, there's no RAP information in here. It's all satellite is coming from that, because this is the difference between satellite and the forecast. And you'll see that, so it actually shows where the satellite data is, it's everywhere. And for this case, very clear over the Wisconsin, Northern Illinois region. Far different than over the East Coast, where it's very stormy, lots of rain and so on, where the satellite data, as well as the model, shows very unstable conditions, the red areas here. And you also see a lack of satellite data here, the white areas. But in any event, this is what we got to live with until we can actually get a real hyperspectral sounder in geostationary orbit. So with that, I think that's enough. I want to conclude, and I'm looking forward to lifting a beer with Hank, as Hank is doing here, to congratulate him on the very major successes that he's had during his exceptional career as a scientist. And amongst his many accomplishments in the planetary sciences, which you're going to hear about, and climate research programs, I believe that Hank is best known internationally for his unsurpassed expertise and leadership in the hyperspectral infrared interferometer program, or 4A transform spectrometer, where he's really recognized as being the lead in that particular area. And he's the one who made our dream of being able to sound the atmosphere with high vertical resolution come true. And I'm not just saying that to be nice, Hank. It's true. You really did it. And on a personal note, you know, it's really been an honor for me to work with you over these past 41 years, and we're still at it. You know, the one thing they can say about us is that we got perseverance. But we've also had a lot of successes thanks to your leadership. And one of the things is that you've been a wonderful inspiration to me because you're so optimistic. And you know, I saw a cartoon once that always reminded me of Hank. It's a cartoon that shows a little boy sticking his head above a bunch of horse manure. His head is coming out of this manure. There must be a pony around here somewhere. That's Hank. He's always making the best out of a bad situation. And you're not only, you know, a world-class scientist, but I also appreciate you being a close personal friend. So Hank, thank you so much. I really appreciate it. Love you, man.
It's only been mutual.
Bill, thank you for that. Don't unhook yet. I want to open it up for any questions or comments on your presentation on the many years you worked together with Hank. Anybody? Dave Turner.
Bill, Hank, how many times did you get into methodological arguments about what you were actually observing?
We had our debates. But we don't argue too much, really. We're very complimentary, I think. That's. Yeah, right. I don't think we disagree too much. Well, we have our own particular areas of expertise. Who am I to argue with Hank over, how to implement something technically? I trust the man.
I think through your unbounded energy as a team, a lot of good things happened. And in my physics career, at least, I've never witnessed where experiment and theory were married so closely together, where with the FTS measurements of the spectrum, people like Dave Turner, Tony Clough were able to improve the theory, line widths, line strengths, mixing, and it was just a rapid progress towards understanding the spectrum in the infrared. So my congratulations to you and thanks, because in my talk you'll see that I'm trying to borrow this without doing the work. At any rate, Fred mentioned that there were going to be readings in the agenda right now, and that's going to be during the banquet tomorrow evening. And we've collared some of you already to have some comments that you want to make or that we're making you make. Others of you, if something gets triggered in the next day and a half, or you'd like to make some statement to Hank's work or your interactions with him or what you remember, we encourage you to prepare that in your mind as much as that works. And we'll have an opportunity tomorrow evening for you to make some short comments. And now the agenda calls for us to take a break, and then we will come back at 3:30, and Dave Tobin will chair the session, and we'll hear from some of Hank's explorations of the planets and some of his travels in the high spectral resolution.